Hi everybody, I am Pascal Urien, professor at Telecom Paris, Grande École in Saclay, Paris, France, and the subject of this talk is personal HSM privacy for subscribers in 5G, 6G networks. This paper presents the concept of personal HSM for 5G, 6G networks. In cloud infrastructures, hardware secure modules provide cryptographic services, typically for banks or web companies. We introduce the idea of deploying USIM-like devices in edge or core data center in order to support on-demand application. We define two planes, first for application providers using legacy ISO 7816 standards, and second for subscribers based on TLS 1.3 secure channel. We present an experimental platform that could be integrated in emerging embedded secure element ESC. We detail secure element communication stacks and attestation procedures that transfer exclusive ownership of secure element from application providers to subscribers. As is illustrated by these figures, 5G networks work with 6 security domains. The first one, network access security, is a set of security features that enable a user equipment to authenticate and access services. Universal Subscriber Identity Module, USIM, is a root of trust for 5G, 6G networks. Authentication vectors are produced by home networks and checked by USIM, thanks to shared secret key. USIM logical interface relies on ISO 7816 request response, that's to say Protocol Application Data Unit, APDU, even for new form factors such as integrated SIM, iSIM, or embedded SIM, eSIM. Authentication credential repository and processing function computes from C key and I key values produced by USIM, a set of keys used by multiple entities. Smart Secure Platform is a future extension of today's USIM functionalities. Legacy secure element is based on ISO 7816 standards. SSP support new physical layers such as inter-integrated circuit or serial peripheral interface. In this context, Ethernet or ISO 7816 data layers could be used. SSP common layers may provide TCP/IP services. Presentation layers could be based on TLS or Global Platform Secure Channel Protocol. Applications are associated either to legacy APDU interface or to HTTP CoAP protocols. In summary, SSP provide two new use cases for USIM, networks node, and non-APDU application interface. Hardware Secure Modules, HSM, is a piece of hardware whose security requirements are defined by FIPS 142 standards, security requirements for cryptographic modules. 4 security levels are defined. HSM price depends on security levels and performance in terms of transactions per second. For example, a device with security level 3 costs $30,000 for 3,000 transactions per second. HSM supports a few partitions, so the number of users is limited. Azure dedicated HSM costs about $5 per hour. Azure Key Vaults, for example for elliptic curve, cost $5 per month plus $0.03 per 10,000 transactions. A typical use of HSM in data center is private key storage and use for web server identified by their certificates. In payment context, HSM performs cryptogram verification based on secret triple-desk keys. In 3G, 4G, 5G context, HSM relies ARPF cryptographic operations. In summary, HSM, mainly single tenants, compute thousands of transactions per second, that's to say signatures, cryptogram, or authentication vector. PKCS11 is a cryptographic API, commonly referred as cryptographic token interface, cryptokey. It is widely supported by HSM. It organizes cryptographic resources according to slot and token hierarchy. Originally, the slot represented a smart card reader and the token a physical smart card. Sessions are opened with a coupled slot token and are authenticated by PIN codes or challenge response mechanism. The PKCS 15 standards describe the logical structures of cryptographic token, typically a smart card, according to a set of directories and files. The emergence of 5G core networks in many countries' critical infrastructures should require an augmented level of security against cyber attacks. In order to fulfill these new requirements, some networks manufacturers propose HSM devices typically used for ARPF procedures, but also for other use cases in which user privacy is required. As mentioned earlier, HSM are mainly designed for single-tenant operations. Contrary to USIMs, they don't aim to provide tamper-resistant computing resources at individual square. The idea of personal HSM is the deployment in core or edge networks of secure elements dedicated to 5G, 6G subscribers. Similarly to SSP, we propose a new stack for USIM. A legacy communication, left side, for global platform services based on APDU. New communication protocol, right sides, for user of service based on TLS 1.3 servers and presentation layer such as concise binary object representation CBOR. Data layer could be based on I2C or legacy ISO 7816 standards. A personal HSM server manages two TCP/IP daemons, first for global platform loaders, racks, and second, TLS from server for subscriber services. Remote APDU Call Secure is a protocol dedicated to APDU transport for grid of secure elements. Within the grid, each secure element is identified by Secure Element Identifier, SEID, for example, a slot number or an I2C address. Sessions between rack server and clients, secured by the TLS protocol, are mutually authenticated by X509 certificates and associated private keys. Rack is an ASCII protocol that uses command line, including SEID. Client credentials rely on access control list bound to identity provided by X509 certificates. Today, cloud architectures use TLS from server as router to TLS backend servers identified by their name, the server name SN. Each secure element, TLS pressure key layer, is associated to a server name, the secure element name SEN. The SEN is, for example, included in the historical byte fields up to 15 bytes of the answer to request ISO 7816 message returned upon reset. The uniform resource identifier looks like scheme S //sen://psk@server.com:port/?query, in which query is a message according to the representation layer syntax defined by scheme S. In our prototype, Secure Element Processor, SEP, implements a bridge between ISO 7816 and I2C protocol. Our personal HSM server is based on I2C bus. Each SEP has an I2C address and implements a protocol similar to those supported by SC50 secure elements. I2C frames comprise a 3-byte header, NAT PCB length, an optional payload, and 2 bytes CRC. Mine command resets the secure element and returns historical bytes or send ISO 6816 request and pull for response. When the secure element has no data to send, for example because an ISO 7816 request is in progress, the SEP returns the specific NAT with an empty payload. Here is a short illustration about on-demand application and attestation procedure. The user requests the service provider to deploy a TLS-SE application. The service provider downloads the application in a particular secure element identified by its SEID. Upon instantiation, the TLS-SE app generates a pair of public and private keys. Thereafter, the application provider binds SEN to SEID thanks to a dedicated racks command. At this step, the TLS-SE server is a TLS node identified by its SCN and TCP/IP socket. The application provider reads the public key and generates a certificate, that's to say the ECDSA signatures to integer of the public key hash with the certification authority private key. The application provider transfers PSK, that's to say PSK provider, and SCN to user. The attestation procedure transfers TLS-SC property to user. It relies on the fact that TLS-SC server can manage only a single session at a given time and cannot be cloned. The user opens a TLS-PSK session. According to TLS 1.3, an unchecked secret HS is shared between client and server. The user reads the public key, reads the certificate, and checks its content with the certification authority public key. It generates a random value, whose value concatenated with the unchecked secret is signed with ECDSA algorithm by the TLS-SC app private key. The user checks the signatures with the TLS-SC public key. Upon success, the user modifies the PSK. The TLS-SC device is now ready to use. Thank you for your attention.